First example that I would like to present to you is a decision dilemma. A while ago in suburban Chicago, there was a couple that won the Powerball. They were pretty lucky. They had to choose between a single lump sum of 104 million or 7.92 million per year. That would be 198 million paid over 25 years. They chose the lump sum. They opted for the lump sum. The question is, did they make the right choice? And those are some of the questions that can be best answered after we equip ourselves with all the technical tools that we need when we're dealing with technical economic analysis. So the option A was to opt for 104 million now. Option B was to annually get paid 7.92 million for 25 years. So in order to make such a decision, what is it that we really need to know? We need to know the value of money at different point in time, because we want to know 25 years from now how much 7.92 that they collected per year would worth. So to do this, we need to develop a method for reducing a sequence of benefits and costs to a single point in time. In other words, we need to bring everything, the value of the money to a point either today or at 25 years or 10 years from now or at a specific point in time, so we can make a comparison. Then we will make the comparison based on that. So why do we need to do such a thing? Because, again, money has a time value because it can earn more money over time. First, if you have $100 million today and you invest it wisely, it is very likely that money would bring more money. Whereas the less that amount would be, obviously there would be less interest on that. So also, again, we are looking at fundamental concepts. Money has a time value because its purchasing power changes over time. And that is called inflation. The change in the purchasing power of the money, in order to put it in simple terms, is called inflation. What is an interest rate? Time value of money is measured in terms of interest rate. That's the rate in which the interest would actually be calculated to the money. And interest is the cost of money. Borrowing money has a cost, and that is, again, the cost to borrower or earning to the lender. So both sides of the equation, whether it's a borrower or the lender, they use interest because interest is the cost of money. So it's important to realize these four fundamentals when we talk about time value of money. So another example, again, somebody's taking a loan out today, $20,000, and there are two plans in front of him. One is to, for both plans, pay $200 up front. One of them, over 5 years, pay $1,141.85. So over the 5 years, or to pay nothing, and at the end of 5 years, pay $30,772.48. That is $10,772.48 more than the original loan. Okay, so the assumption is, again, the loan amount is $20,000. There'd be some kind of a fee called origination fee of $200, and the interest rate is calculated at an annual percentage rate, APR, of 9%. Again, we are going to talk about the difference between annual percentage rate and the pretty much interest rate and all that, and how they're calculated. Interest rate calculated at the different frequency would earn different values for the borrower or the lender. So that brings me to the concept of cash flow diagram. In order to best describe the loan, again, $20,000 with $200 origination fee or some kind of a fee, and that would be $9,800. We show this type of a problem on a diagram in which there are two arrows associated with this diagram. One is, well, there are two directions of the arrows associated with this diagram. One is pointing up to your page, the other one is pointing down to the page. The money that is still outstanding, or the money that's been borrowed, it shows on the arrow that's pointing upward. The money that actually get paid or installment plan or being subtracted from the original, that will be shown with an arrow downward. Usually the downward arrow is the money that need to be paid over time, and the upward arrow shows the money that is either has to be borrowed or is being borrowed or it is present. Again, over the years, for each year, we associate the number with the year 1, year 2, year 3, year 4, year 5. And note that there is a year 0 here, and that 1 is really not at the end of the first year. Well, it is at the end of the first year, but that 1, don't get confused, that 1 doesn't really show the year. It shows the end of the year. So this is year 1 from here to here, and from 1 to 2, that's year 2. From 2 to 3, that's year 3. From 3 to 4, that's year 4. And from 4 to 5, that is year 5. So I want you to be clear on that. So it's important to show such calculations in what we call a cash flow diagram. Cash flow is a simple diagram that shows the flow of the money, flow of the cash, whether it is to be paid or whether it's being borrowed, depending on the direction of the arrow. I highly encourage you to practice with some of these cash flow diagrams as we go through this course. What is an end of period convention? An end of period convention is just what I just described to you, 0 to 1. And that 1 is actually the end of the interest period. And within that 1 year, there could be multiple points in which interest are calculated on the money on the original amount. So the interest period is not necessarily at the end of the year. It could be calculated daily or monthly or quarterly or every 6 months or what have you. So what are some of the methods of calculating the interest? Again, there are simple interest and there's a compound interest. Simple interest is pretty much an interest rate that only applies to an initial sum or the principal amount. Rarely that is used in the real world. The real money managers and bankers, they use compound interest. Compound interest is used in almost every calculation, economic calculation that is performed today. It's the practice of charging an interest rate to an initial sum and to any previously accumulated interest that has not been withdrawn. Shortly, I'm going to show you an example. This is an example of a simple interest. The principal amount is shown here as P, and the interest rate I is also marked here, and is the number of interest periods. An example is we borrow $1,000 and $1,000 needs to be paid back over 3 years. The interest rate is 8%. How much do we need to pay back at the end of that year? So year one, the ending balance is $1,000, assuming 8%, so $80 would be the interest. So at the end of that year, it will be $1,080. To this $1,080, another $80 would be pretty much calculated as interest earned, and that would be another $1,160 to this $1,160, which would be left at the end of year two. There'd be another interest of $80. Note that the amount of the interest earned here has not changed over the years, although the money at the beginning balance has changed. So this is a simple interest. The formula for simple interest is F is P plus IPN, in which the principal amount is P, I is the interest rate, N is the number of interest periods, and F is the total amount accumulated at the end of period N. So let's compare that with a compound interest. Again, this would be charged to an initial plus the accumulated amount. So let's take a look at the same example, same period, same interest rate, same principal amount. So at the end of year one, well, end of year zero, which is today, $1,000 has been borrowed. The interest earned on that money, or interest accumulated on that money at the end of year one is $1,000, $80 accumulated one time. N is number of interest periods, and that would be $1,080. So the 8% now, this $1,080 at the end of the first year would be the beginning of the second year. Now, instead of $80, it's going to earn an interest of $86.40. So now we're taking 8% of this particular amount. And we add $86.40 to $1,080. At the end of year two, the money would be $1,166.40. And the next 8% interest would be earned on this amount, $1,140, this amount down here, which would be carried from the end of year two to the beginning of year three. Now the interest is $93.31. The interest that's earned is $1,259.71. Okay? So compare that to $1,240 for simple. So it's about $1,240, it's about $20 more in interest, the same interest rate, but the way it's being calculated is different. So compound interest rate would be much more than simple interest. Not the rate, but compound interest, the way it's being calculated, the money that is earned by a compound interest would be more than the money that was being earned through the process of simple interest calculation. So if we take a look at this, as you can see, we need to formulate the compounding process. Again, $1,000 today at the end of the first year with 8% interest rate would be $1,080. This $1,080 would be for the beginning of the second year. Again, it will be $1,166.40, and so on, as I just showed you. The formula that we can come up with here is F is 1,000 multiplied by parentheses 1 plus 0.08, which is the 8%, to the power 3, and that would be $1,259, so almost $1,260. So the compound interest formula, this is perhaps the most important formula when you are dealing with finances and interest rate, when you're buying a car, when you're buying a refrigerator, when you buy a house, every time you borrow money or lend money. This is the formula that's used, and you would learn in this class how this formula can be manipulated using different values of n with the same interest rate. The higher the number of n, that means the power here is higher. The exponential power would be higher, so 1 plus I to the power n, and the bigger the n, the larger would be f. So P is the present worth of the money. At the end of year 1, we call the future worth as F1 is P multiplied by 1 plus I. N is 2, F2 would be F1 1 plus I, P, or P multiplied by 1 plus I to the power 2, and so on. If we continue this n times, okay, so as n is approaching n, a larger number, then the power of 1 plus I, the parentheses, would keep increasing by n, by the number of n. So n is 2, 1 plus I is to the power 2, and so on. So if we follow this formula and carry it down, f would be P times 1 plus I to the power n. Again, this is a very important formula that you need to be fully aware of how you can actually work with this formula. So in different science, we have different in different fields, we have different formulas. For calculating force, we have FMA. For calculating the voltage, we have I times current times the resistance. For E, we have MC squared, energy mass times the speed of light squared. The fundamental law of engineering economy is F is P multiplied by 1 plus I to the power n. And that is perhaps the most important formula that we use in engineering economy. This is called the fundamental law of engineering economy. So nobody should ever forget this law, because this is very applied and it can be used pretty much in every type of transaction when we're dealing with interest rate, future worth, present worth, and the number of periods of interest calculation. So, according to Albert Einstein, the compound interest is the greatest mathematical discovery of all time. Let's take a look at good old Warren Buffett. The Berkshire Hathaway company went public in 1965 at $18 per share. It's worth today, this is as of August 22, 2003. Each share, it was worth $76,200. That's as of August 22nd, 2003. The annual compound growth is 24.58%, almost 25%. The current market value is $100.36 billion with a B. And if he lives till 100, we hope he does. Back in 2003, he was 73. And what would be the value of his company? Warren Buffett is perhaps a great example of someone that is very talented in picking stocks and be a very successful businessman by his own accounts. So if the company's stock will continue to appreciate at an annual rate of almost 25% for the next 27 years, it's going to worth what? 37.9 trillion with a T dollars. That's an astronomical figure when we're dealing with money. So let's do a practice problem before I can end our discussion today. Problem statement: if you deposit $100 now, assume N is 0 and $200 2 years from now, and it's 2, in a saving account that pays 10% interest, how much would you have at the end of year 10? Okay, so let's draw the flow, cash flow diagram here. And as you can see, we put all the numbers from 0 to 10, and we use the formula. Compound, the interest rate is 10%, so this would be the I. N is they're calculated at the end of each year, so we have 10, and capital N equals to 10. And we want to know what the future value is, and the future value would be, again, $100 now, and $200 2 years from now in a saving that pays 10%. So now it's $100, so we need to see what would be the the future worth at the end of 10 years for the $100. Also the $200 that would be deposited 2 years from now. What would be, how much would that worth 8 years after that, which is 10 years from now? And that would simply be $429, and the total would be $688. Again, we use the compound interest method, the power to demonstrate the power of compounding. The other problem, as the last problem, is if you consider the following sequence of deposit and withdrawals over a period of 4 years, if you earn 10% interest, what will be the balance at the end of the 4th year? So today, $1,000. At the end of year 1, 1,000, and another 1,000. There will be withdrawal of $1,210 at the end of year 2. At the end of year 3, there will be another $1,500 deposit. What will be left at the end of year 4? Again, the interest rate is shown here. As you can see, 1,100, the interest rate is 10%, so that 1,000 at the end of year 1 would be translated into $1,100. There'll be another deposit at the end of that year, so 1,000 would be added to 1,100. Total would be 2,100. That's at the end of year 1. That's the balance. At the end of year 2, assuming again the interest rate that's given in the problem, the $2,100 would be $2,310. There would be a withdrawal of $1,210. This would be the balance. There would be an interest, again, calculated on that balance at the end of year 2, which is the beginning of year 3. And that money would be translated into $1,210, assuming the interest rate is given at the end of the 3rd year. And there would be a $1,500 deposit, $2,710. At the end of the 4th year, there would be no deposit between year 3 and 4. At the end of the 4th year, assuming the interest rate that's given in the problem, the balance would be $2,981. And the solution also demonstrated here in the form of a table, again, pretty much illustrating the same concept that I just went over. That brings me to the end of this topic.